This is the third example problem, a user code problem called Haybale stacking. And this problem illustrates the notion of a difference array. Here's a problem statement. So we are given n empty stacks, and n can be up to 1 million. And the call Bessie is given a sequence of k instructions, and k can be up to 25,000. Each instruction is of the form of two numbers, and the meaning is Bessie should add one new Haybale to the top of each stack in the range AB. So A and B are given at the range. And after all these k instructions are executed, the question asks us to compute the medium height at the end. So let's look at the sample. So we have n equals 7, so we have 7 Haybales indices from 1 to 7. So here this question asks to this question uses a 1-base index instead of 0, so index start at 1. And k is 4, so there are 4 instructions. The first instruction is a 5-5, so I use the blue color to indicate this instruction. And then after this blue color instruction is executed, then we have the 1 Haybale is added at location 5, index 5. So basically here, this guy. And the second instruction is 2-4, so it's a light blue. So then after that, we have these 3 added, and then after that we have a green from 4 to 6. So we add the 3 green one corresponding to here, and then after that we have the last instruction is to add 1 each to 3 to 5, and we have the yellow ones added. So after this we have after all the 4 instructions, we have the height are 0, 1, 2, 3, 3, 1, 0. If we sort them, this is what it is. And then the medium of this height is 1. So there are 3 height smaller than it and 3 height bigger than it. So now let's think about how to solve this problem. So the natural way is we maintain the array of all the stacks. So the array have 1 million elements, which up to 1 million elements, which is fine. And then we just update that. Every time we get instruction, we add 1 to all these corresponding cells. The problem, of course, is there are too many of these instructions. So each instruction, and there are up to 25,000 instructions. Each instruction could potentially add 1 million things. I need to update up to 1 million array elements. So then that's not going to be efficient enough. So the question is, how do we make that efficient? So this question is, we are doing a lot of update, but we are not, the query only happened at the end. So in a sense, we don't need to be able to recover the exact state until at the very end. And also, every update, we are updating a range. So we are adding a number to a range of the number. So the update is not to a single element, but rather to a range. So these features means that it can be solved using what's known as a difference array. So the idea is we don't keep track of the actual height of each of the Haybale. Instead, we just keep track of the difference of adjacent height. So for every element, we store what's the difference of the height in this place to the previous one. So if we have an array, then the difference array can be defined in this way. So the first element is just the same as the original element, and then each of the later elements is defined as the difference between the two corresponding elements. So the advantage of using difference array representation of the array is range updates are easily done. So they are storing exactly the same information. So whether you are storing the actual value or you're storing the adjacent differences, the information is the same. You can construct the one from the other. And we choose to represent the information using the difference array is because range update can be done very efficiently, because a range update means only 2 update in the difference array. Because the range update is saying, let's say a range update from 3 to 10. So then that means at the difference between 3 and 2 is changed by 1. But the difference between 3 and 4, 4 and 5, 5 and 6, and so on, they are not changed. Only the difference between 10 and 11 are changed when we add the same height to all through 3 and 10. So because of this, in this problem, the efficient solution is to maintain a distant array, and then we reconstruct A using linear time. So this slide shows the difference array information. So in the beginning, in the beginning, we have all 0. So the update 5.5 saying that now at the position 5 we will add 1 more Haybale. So then that means the difference between 4 and 5 need to be +1. And because the additions end at 5, the difference array at 6, it will become -1, because 6 will be 1 lower than 5 because we just added 1 to 5. So the difference array is +1, -1. And the update at 2.4 means that in the difference array we need to add 1 to 2, because stack 2 is 1 higher than stack 1. And because the addition stop at 5, so then we need to add -1 to the difference array at 5. So at this point, the difference array state becomes 0, 1, 0, 0, 0, -1, 0. So essentially saying that from 2 to 5, we have a 1, and everywhere else we have 0. And then similarly, we update that for the next operation and the next operation. At the end, the difference array we have is this state. So we have 0, 1, 1, 1, 0, -2, -1. And this means that the final height is 0, 1, and here is 2 because we add 1 to the previous one, so we get 2. And then we add the difference 1 to our previous one, 2, we get 3. And here is 0, so this remains at height 3. And here we have -2, so the height becomes 1, and then becomes 0. So you can verify, compare with this picture, this is exactly the right state. So the algorithm is we maintain a difference array, and then at the end we will reconstruct this height array, and then we will compute its median, and the median can be computed by sorting it and then return the element exactly in the middle.